On April 10, 2019, researchers unveiled this image, the first ever picture of a black hole. But what is a black hole? And why is this blurry picture such a big deal? To answer these questions, let's first look at their origins. Stars. In their cores, hydrogen atoms go through fusion to create helium atoms, releasing a ton of energy in the form of radiation. This radiation pushes back against gravity, maintaining a balance. For stars with significantly more mass than our Sun, the gravity allows for larger and larger elements to undergo fusion until they reach iron. Unlike the elements before it, the fusion process that creates iron does not create any energy, leading to less total radiation being produced and causing the delicate balance between gravity and radiation to be shattered. As the core collapses inwards, the star dies in a supernova explosion, resulting in the formation of a black hole. In addition, all of the natural elements heavier than iron, including krypton, the home of Superman, are created in this explosion. The most popular idea of a black hole is that it works like a cosmic vacuum cleaner, sucking up everything around it. Instead, imagine a ring around the black hole. This ring is called the event horizon, and once you go past it, you have to be traveling faster than the speed of light to escape its immense gravity, which is the only unwavering traffic rule of the universe. If you looked at a black hole, you would really just be seeing the event horizon and all of the mass rotating around it, also known as the accretion disk. In order for you to see something, light has to bounce off of that object and then into your eye, but the light isn't actually moving fast enough to escape the gravity of the black hole. At the very center of this black hole is the singularity, a single point where all of the mass is concentrated. Now you may be wondering, what's it like inside? So let's imagine you fell into a black hole. Because objects with extreme mass, like black holes, bend space-time, an outsider would see you slowly fall into the center of the black hole, while from your point of view, you see the rest of the universe and fast forward. However, that assumes that you would survive long enough, which you wouldn't. The immense gravity inside the event horizon would tear your cells apart and heat you up until you became a one-atom-wide stream of plasma. This process is very scientifically called spaghettification. But even black holes have a lifespan, and even they can die. Space isn't really a vacuum, but it's filled with virtual particles and antiparticles that randomly pop into existence as pairs. In space, these particles cancel each other out and nothing really happens. But when these particles form on the edge of a black hole, with the negative particle inside and the positive outside of it, they cannot cancel out and the positive particle becomes real. This process is called Hawking radiation. Because of the negative particle's negative mass, the black hole loses a small amount of mass. Eventually, this leads to it undergoing evaporation, during which it would release abrupt explosions of gamma rays. Studying the Sun has led to numerous discoveries, including critical concepts of gravity and the discovery of our own revolution around it. Since then, we've been able to take humans to the Moon and back, and land our very own robot upon Mars. The next step in our understanding of the galaxy is black holes, and we've begun this already by photographing one. But if we keep studying them, they could take us further than our wildest dreams.